Hello there, thank you for joining me today. We've got on the bench a bandpass filter made by Bird Corporation, and this is basically the specification. It has an N-type plugs on either end, but it says there Decibel Bird Incorporated USA, model number, low pass filter 50 ohms, 300 watt rating, and a frequency range of 144 to 174 megahertz. It's quite heavy, and what we're going to do as part of this measurement series of videos on components that I'm going to start doing is we will look at doing measurements of the characteristics of this filter on the different types of test instruments. So today we'll use the IFR 2968 radio communications test set that's got tracking generator on it. We've got the monitor replicated there so we can see things nice and easy, and we'll set up a measurement. The first thing we'll do though before we measure any filter or device is what we'll do is we will set up the instrument, which I'm going to detail next, and then what we will do then we will check the cables. So we'll have essentially join the two ports together there, the RF ports. We'll join these two cables together and make sure then when we calibrate that what we're getting out is what we're giving out is what's coming back in, so that we're not going straight into a measurement of a device which then may give a different result if we're not sure that the reference levels and everything are all set up properly and the instrument's calibrated correctly. So we'll do that next, and then we're absolutely certain that when we do connect this device up, then what we're seeing on the screen is what we're actually getting in reality, and we're not being led down a garden path. So we're back in a minute. Okay, so now we're ready to set up the instrument. We've joined the two cables together, and we're all torqued up and everything. So I think the first thing we'll need to do on the on this instrument is to select the RF test option. So we'll do that. We'll select RF test on here, and then we've got the selection there. You can either do an audio one or a full function multimeter. I think I've pressed the AF test instead of the RF test. There we go. RF in out test at the top, which is what we'll do. We'll select that, and then we've got that. Then we get the spectrum analyzer up as well, which again is this key here, spectrum analyzer. Then in there we can expand the screen as well, so that we've got that on the screen. We've got a track gen somewhere on here, and I can find it. It's been a while since I've used this test set. Wonder if it's. Let's just go back to that RF test again. Right, RF input output test, and then. Just trying to find out where we are with it. Spectrum analyzer. So I was in the right area. Spectrum analyzer. Expand. And then there was markers expand on and off track. There we are. Couldn't see that. But we noticed that the signal there. There's already a signal coming out on the signal generator. What we do first of all is we'll just set up under RX test, we'll just set up the RF gen level. We will put the meter on down there for outputting. We'll do, because obviously this port's a higher level RF output port than this one is. The signal generator I think can only go up to -10 or -15 dBm on here, where we're going to use 0 dBm, 0 dBm is a good rule of thumb, a marker for making RF measurements. So we'll need to send a signal out of this, which is why this arrow's lit up there, and then we'll adjust the RF gen level to 0 dBm, and then now we're outputting that, so that we've already set up the reference level now of the RF signal coming out. So now we can go back into the RF test feature. It says here the signal output input level has changed, which we know, and then we can go to track on, and then basically it's saying minus 10 dBm. I was expecting to say 0 dBm, so that's interesting. Let's have a look and see what we can do about that. RF test again. RX test. Oh, it says minus 10 there, that's why. I wanted it at 0 dBm. Don't know why it keeps changing things. You put things in and it, you know, it then changes it back. You know, unless it's because of these ports were switched the other way around. That could be it. These ports here, when I go back to RF test, yeah, it turns them the other way around. Daft thing. So let's go back to the RF. Now we're generating a signal out there. RF input output test. RF gen level 0 dBm. Maybe it'll listen to me now. RF test again. Then we go to RF input output test. Then we go to spectrum analyzer again. Then we go to, after we've done that, spectrum analyzer. I'm pressing the right buttons, expand, and then we go to track gen on, and now we've got 0 dBm on the top line, which is what we can see there. That's 0 dBm. We can confirm that by putting the markers on, and again the level there, it says minus 1.5 something dB, which is acceptable because that's what these cables, there's a good 2 meters of coaxial cable there going up, a meter each, so you know that's acceptable. At that I'm not going to worry too much about that. So our cables are all nice and tight and snug and everything, and so now we can connect up, and we'll now connect up to this bandpass filter, and then we'll commence the next stage of the measurement. Okay, so just a quick lesson really regarding particularly SMA cables. I seem to be more prone to this than other types of cable, is that if they're not torqued up on these connectors, then unfortunately you can get erratic RF readings. Earlier we had the issue where we had the marker at 1.5 dB loss, 1.6, and that was because the cables weren't tightened up appropriately. Now you can see it's 0.3 minus 0.3, 0.5, call it dB loss in the cables, which is acceptable obviously for the length of cable that we're using. So we can, if we want to, offset that by increasing the RF level just very slightly to get that to 0 dB, so then it basically factors in the cable losses. So we can actually do that. But for this measurement, because it's obviously a VHF and there's not going to be much loss at that frequency, I'm just going to basically connect it straight into this this filter, and then we can measure it. Okay, we've connected the cables up now. Notice that on this bandpass filter in particular, it doesn't give you an in or an output port identification. Some filters do have an in and out designated, so you know that's something to take note of if ever you get a bandpass filter, whether it's got an input and output port assigned, and then obviously take note of that. This one doesn't have for whatever reason. So okay, we've connected it up. We're getting a flat line across the top because the bandwidth is currently marker 1 is set at 140 whatever it is megahertz. If we can have a look at that, what is that? Let's have a look. 149 megahertz. So we can then alter the resolution bandwidth of the tracking generator. Oops. So now we can see that we've got a almost 0 dB loss, really, all the way to this point before it begins to rapidly fall off. So if we can adjust the marker, so we'll move marker 1, and we'll just move that in frequency, and then we can then look at that. So that's 100, and it says there on the specification of the filter 144 to 174. So if we set marker 2 right at the start frequency there, obviously that's 50 megahertz, 70, 80, 90, 100, 144. So it's actually got a pass band a lot lower than 144 as well. And then obviously marker 1, if we move that ever so carefully, marker 1, and obviously right on the end there, just before it disappears off the end of the earth, and that marker 1's at 170, 178 megahertz, 178.4. So we can find the 3 dB points as well on there. So if we just move, looking at 1 dB, minus 1 dB loss there according to that, which is, you know, just here between half a dB to 1 dB. So if we take that down to 3 dB points, that'll be like minus 4 if we include the 1 dB loss. Then that will give us the bandwidth there, and where the cutoff frequency really is about there. So we're looking at round about 183 megahertz, I think it is. Let's see if we can zoom in. Yeah, 183. So that's actual loss at the reject frequencies. If we carry on, we can see that it's like minus 20 dB there. It's like it hits the noise floor about there, minus 40 dB at 242 megahertz. Let's have a look. So yeah, it's goes down about minus 40 dBs rejection, so that's its reject limit. So some filters, you know, depending on the types of filter they are and the quality of them and how they're designed, can achieve a really low level attenuation. Some are high level attenuation. All depends on what they're designed to do, whether they're designed to suppress harmonics, whether they're designed to reject another frequency totally, for example, like in a duplexer filter, where one's tuned to pass a frequency while the other side of the filter is tuned to reject a signal, so therefore the rejection needs to be quite high. And this is where you see differences between some filters. Some filters will go right down into the noise floor at the bottom. A really good quality, more expensive filters tend to do that with the design characteristics. Other filters will have, say, a 40 dB rejection, as this one does, or some will have 60 dBs rejection. That's quite common, particularly at VHF frequencies. A lot of cavity filters, barrels and tunable filters tend to have around about up to a maximum of about 60 dBs. But there again, you know, it all depends on the type of filter it is. Generally, the more you pay, the higher the quality that the filter will be. But in this circumstance, we've got a 40 dB rejection outside of the frequency range of the 2 meter emitter band. So that gives us an indication, really, you know, that we can use this basically from 50 megahertz up to, you know, 100 and well, basically 170 something megahertz, and then it tails off. So it'll be very good at suppressing harmonics as well, obviously, that occur higher up in the frequency band. The doubles of frequencies, the second harmonic, third, fourth harmonic, etc., will be attenuated by at least 40 dBs there. So that's quite useful if you're obviously using a lot of RF power on the 2 meter emitter band on 144 megahertz, 145. It would obviously suppress any harmonic content that's coming out. A typical example of using that in an amateur radio setting would be where we're using, say, a ham portable radio into an external RF power amplifier that would, you know, obviously amplify the signal incredibly high. And now also a mobile, perhaps a low power mobile that does 5-10 watts into a 300 watt linear amplifier, for example. In many non-commercial aspects, amplifiers that are designed for amateur radio tend not to have very good bandpass filter characteristics on the output of the amplifier. When they design radios, amateur radio transceivers, or PMR radio transceivers, for example, the radios are designed with the bandpass filter circuitry within the radio transceiver, so that it meets the specifications of the regulatory bodies of the country where that transceiver is going to be used in. So it doesn't cause interference to the users, basically. However, when you buy a separate amplifier, for example, a linear amplifier that's available, you know, obviously for CB radio or for amateur radio, that kind of thing, made by companies like Benos and other popular manufacturers, they do have some bandpass filter capability in them, but it's not inherently good. And unfortunately, it's often the case where you'll be transmitting hundreds of watts from an external separate RF amplifier, and unfortunately, along with that fundamental signal being obviously, you know, the desired frequency you're wanting to amplify, there will be staggeringly high harmonics that go with it, and some of these harmonics are so bad that they can cause mass interference elsewhere in the radio spectrum. So that's why you would employ something like this on the output of a linear amplifier, so that it would basically attenuate off you know, any harmonics that are appearing higher up the band. So this is obviously a low pass filter because it's passing frequencies that are lower whilst rejecting frequencies that are higher, hence the term low pass filter. Obviously a high pass filter would do the opposite. It would reject the low frequencies and pass the high frequencies. So that's just a little rundown of using the this radio test set, and obviously looking at this filter, and obviously its spec, which we'll be able to look at on Bird's website probably to find out its total spec. So that's it really, little rundown of doing a measurement on the 2968 and measuring a bandpass filter. Thank you for watching the video, and if you like what you see, please subscribe. There'll be more videos on RF components and using different pieces of test instruments and what have you. But till the next time, take care, and we'll see you again.